What's up, bitches? Welcome to another video. Today we're going to learn about transfer functions. This, usually, it should be your last chapter for your modeling and analysis class. So there's a good chance that you're watching this a few hours before your exam. But don't worry, you're not cooked. I'll teach you exactly what to do to pass. So, in this chapter, it's a little bit complicated, okay? But I'll explain to you guys what you should know to answer your exam questions. You have your you have your input response, your input, well, you have your system inputs, whatever you're putting, or it could be U of t or F of t, and Y of t is basically your system's response. System response. It's basically whatever the simulation gives you as a result, and this is your input. Okay? So, your transfer function is h of s, which is equal to y of s divided by u of s. That's your transfer function. That's it. Transfer function over here. That's what it's called. Transfer function. It's equal to like the relationship of your system's input response. It's a relationship between your system input response, which is here, and your system's response. Okay? In the Laplace domain, okay? If you don't understand that, don't worry. You don't need to understand this, okay? You just have to keep in mind this equation right here, okay? Next, one of the first things that you're going to learn in this chapter is the following equation, okay? Now, personally, when I was taking this class, this was not in my final exam, but it was in my exercises, so it's good to know just in case. What the fuck is this, basically? That's your damper ratio, or damper constant, whatever. Omega n is your natural frequency. And G of t is your input. Y of t is your system's response, okay? So, in your questions, in your exam or in your exercises, as soon as the question is asking, oh, what's the natural frequency? This equation is the first thing you should be thinking of, okay? So this should be in your formula sheet, but if it's not, you should know this by heart. But chances are it's going to be in your formula sheet, okay? Next, I want to show you guys something, okay? In this chapter, you're going to do a lot of Laplace transforms. So this should also be in your formula sheet. I don't think you should know this by heart. This should be in your formula sheet. Something else that you should know are your partial fractions, because in this chapter, you're going to do a lot of partial fractions. But I'm going to show you guys a trick, okay? Let's say, this should be in your manual too. Let's say you have f, which is a function, divided by s plus 1, s plus 2 squared. Okay. To rapidly find your partial fractions, which is equal to this plus b, s plus 1 plus c, s plus 2 plus d, s plus 2 squared. Okay, this you should know this at this point in your educational not trajectory. At this point, bro, in university, you should know this partial fractions equation by heart. But if you want to find A, B, C, and D quickly, you have to find the poles. What are poles? It's when this function does not exist, which is when the denominator is equal to 0. That happens when s is equal to 0, s is equal to -1, and as s is equal to -2. But whenever you have something squared, those are called repeated poles. So we're going to write it twice. And I always do this just so it's easier to see. When this happens, we can say that A is equal to s times the function, and you evaluate this at s equals 0. Basically, you're taking the denominator and multiplying it, so this goes away. Oops. And then you evaluate it at the pole, which is that. And that's it. You do the exact same thing for b, equals to the denominator times the function, and you evaluate it at the pole. Now, when you have repeated poles, you take the denominator where it's squared here, s plus 2 squared times f, and again, you evaluate it at the pole. Lastly, to find the last partial fraction, c constant, you take the normal, the denominator when it's not squared. So, goddamn. And then you do the derivative. Evaluated at the ds of the exact same thing. F at s equals -2. If you're allowed to have a cheat sheet, I highly recommend you to just like copy this example if you're allowed, because it's going to save you a lot of time. Whoa, 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 whoa. What happened? The last thing that you have to know. What the fuck is happening, bro? My bad, guys. This app sucks. The last thing that you have to know in this chapter are your zero state response. Zero state response. Zero state response is just a fancy way of saying that, oh, your input is equal to 0, or f of t equals 0, okay? If this is the case, there's general formulas that you can follow, okay? There's 3 cases. The first case is if you have 2 normal poles, okay? Then your system zero state response is equal to a certain constant times e to the power of your first pole times t, plus another constant times the same shit, but with the second pole, okay? The second case is if you have repeated poles. So if one of your denominators is squared, then your system zero state response is going to be equal to a constant t plus another constant times t times e to the power of your pole times t. Okay. The last case is when you have complex poles. Okay. In this case, this is a little bit more complicated, but your poles, I'm gonna write them as a pole plus or minus a certain number times I. Okay. Those are your complex poles. Then it's going to be equal to a random constant e sigma t times cos wt. And since this is a trigonometric, you have to add a random angle. Well, not angle, a random radiant. Usually this should be equal to 0 when you're doing your problems. This is very complicated, so there is a chance that it's not going to be in your final exam questions, but it's still good to practice these. And these are all the equations you should know for solving your problems. So let's go and solve a problem just to practice. All right, we're going to solve this problem. This is typically what you should be getting in your exercise problems, okay? So first question is asking you, draw the pole 0 pattern. Okay, so I'm just going to write it again. S plus 1, s squared plus 5s plus 6. So it's asking you to find the poles. So the first thing that should come to mind when you get some shit like this is that you have to factorize it, okay? Here the sum is equal to 5 and the product is equal to 6. So it's 2 and 3. S plus 2 times s plus 3. So your poles is, again, when the denominator is equal to 0. That happens when s is equal to -2 and s equals to -3. The 0 is basically when the function is equal to 0. So that happens when s is equal to -1. To draw this pattern, you draw this omega here, okay? This is basically your, over here on the x-axis is your, what do you call it? your normal numbers, and on the y-axis is your complex plane, okay? So since all of our numbers are real numbers, we can write -1, -2, -3. Your poles, for your poles, you draw an X, and for your 0, you draw a circle, okay? Super easy. If you have complex numbers, some of your numbers are going to be here, but if it's like just like, I don't know, 2i, for example, it's going to be somewhere over here, for example. Okay, let's move on. Next, it's asking you to draw the general form of the zero input response, and after that, an input-output differential equation. Okay, so don't worry about this. This is super easy, okay? Even though it sounds complicated. Just keep in mind that h is equal to y over u. I'm not going to draw the s's. Don't worry about that. This is equal to s plus 1 divided by s plus 2, s plus 3. I'm going to send the u to the other side. Y equals to u, s plus 1, s plus 2, s plus 3. Next, I'm going to take this and send it to the other side. And I'm going to multiply it by y. I'm just going to do it real quick in my mind. Squared plus 5sy plus 6y equals, I'm going to distribute the u, us plus u. Now, I think I wrote, there you go. Now, at this point, we have to do the inverse Laplace transform, okay? To find the input-output differential equation. So, you have over here, you have to use these equations over here. Whenever you have a derivative and you do the Laplace transform, you have to do s times the f, capital F, negative the initial response. So when you're doing the inverse Laplace transform, whatever s you have, the power, that's the derivative, okay? Keep in mind that in this case, we're just going to assume that there's that y of 0 and u of 0 is equal to 0, okay? Just to simplify. So in our case, we just ignore all this shit, okay? What that means is basically, if we have s to the power of 2, that means y is derived twice, plus 5. Here we have 1s, so y is derived once. Here there's no s, so it's just y. Same thing with the u's. And this is your input, by the way. So this is your input-output differential equations. Now to find the general formula, it's basically this, right? We had this transfer function. 2 with our poles s equals -2, s equals -3. You have to follow the zero state response that I told you guys about, okay? When you have two poles, then your system response, the general equation is a certain constant e times this, right? This is what I told you guys earlier. So now that we have the poles, it's sigma 1, sigma 2 is equal to -2 and -3. So your general response is going to be, your general equation, -2t plus another constant times e to the power of -3t. That's it. Next, super easy. You guys see? It's not rocket science. The next question. Use the initial and final value theorem to find the unit step response at t equals 0, t equals infinity. What is the input step response? It's not really important, but it's basically when, actually, I'm not gonna lie, guys, I have no idea what that means. But the final value theorem and initial value theorem basically says that y of the unit step response at t equals infinity is equals to the limit at s equals to 0 of your transfer function, and t equals to 0 is equals to the limit of s that goes to infinity of the transfer function. It's just the opposite thing in the Laplace domain, okay? So I'm just going to do this real quick. S plus 1 divided by s plus 2, s plus 3. Evaluated when s is equal to the limit as s goes to 0 is just 1 divided by 2 times 3 equals 1 over 6. Over here, s plus 1, s plus 2, plus 3. The limit of this as s approaches infinity is equal to 0 because the denominator has a higher power than the numerator. That is the final and initial value theorem. If you have this in your exam, bro, you really have to get 100. It's literally 3 points. If you don't do it, you're like actually cooked, bro. So finally, find y of u and h of t. Okay. Y of u is your system's response, unit step response, okay? So the way to find this, okay, I remember what this is. The unit step response is just a fancy way of saying that your input is just u of t, which is a unit step response. And if you check your formula sheet, you should see that, here it is. Let me get my red pen. That the Laplace function is just 1 over s. So we have everything we need now. Okay. H equals y over u equals s plus 1, s plus 2, s plus 3. So y equals to u, s plus 1, s plus 2, s plus 3. And we said that u is equal to 1 over s. So your y becomes s plus 1, s plus 2, s plus 3. And all we need to do is the reverse Laplace transform. I'm just going to try and speed run this, but basically you have to use partial fractions. A over s plus b s plus 2 plus c s plus 3. Now we're going to use the example that I wrote earlier in this video. A is equal to s times y evaluated at s equals to 0. So it's s times y at s equals to 0. 6. Same thing with b. I'm just going to do it in my mind, but it's just basic algebra, bro. You got this. Negative 2 plus 1. Negative 1. This is 1 or negative 2. Right? Yeah. C is equal to s plus 3. Y at s evaluated at negative 3 equals negative 3 plus 1, negative 3 times 3 plus 2. Negative 2 over 3. Okay, we have everything. Now you just write it down. Y equals to, what did we have? 1 over 6 divided by s plus 1 over 2 divided by s plus 2, negative 2, 3 divided by s plus 3. If we follow our Laplace transforms equations, we can see, let me find it. You have to follow this equation right here. Where is it? This one. Okay. So if we just have to do the reverse Laplace transform, we already have this. We want to go from here to there. So finally, doing the inverse Laplace transform, you would get y of u of t equals to 1/6 e. Is it e? No, sorry, it's 1/6 plus 1 over 2 e to the power of negative 2t, negative 2/3 e to the power of negative 3t, right? If it's just something divided by s, Yeah, that's it. If it's something just divided by s, you just keep it that way when you do the inverse Laplace transform. Lastly, it's asking you to find h of t. This is your impulse function, okay? And unlike, like, you can't just do y of t divided by u of t, okay? It doesn't work that way. The only way to find this is by finding h of s and then doing the inverse Laplace transform of that. So you have to do the inverse Laplace transform of all this shit. Okay. Again, we have to do partial fractions. I'm just going to skip this because I don't want the video to be too long. But eventually you should be getting... damn. -1 s plus 2 plus 2 s plus 3. And then doing the inverse Laplace transform of all this, we get our final answer of negative e to the power of 2t, because it's -1, plus 2e to the power of 3t. And that's it. Good luck on your exams. I hope you guys don't fail and pass. And thank you for watching. Subscribe.